So as we go through this solution, there are a whole bunch of different decision points about different ways that you can approach the solution. All of them, if you do the math correctly, eventually lead to the right answer. But that means that the way that I solve this may or may not be the way that you solved or attempted to solve this. And so as I go through the solution, I would like you to, in your notes, copy my version of the solution down so you have a full set of steps for how to do this. And I'll talk about different points where you could make a different, branching decision on how to approach something mathematically. But I can't show every single possible combination of approaches. And so the first situation that we ran into where we actually had to make a decision was how we write this original expression. We're going to write assuming that down is positive or down is negative. And so we're either going to have positive or negative g minus bv over m. And we made the assumption that down was negative. All right, so we want to get an expression for v as a function of t. So we need to get v equals some function of t, which means that we need to combine all of our v terms onto one side of the equation. The thing is, you might recognize if we're going to deal with this differential equation, I can't just add my bv over m term onto the other side because I'll get dv plus bv over m, and there's no good way to solve that. So instead, we need to divide this entire thing over to the left side. And then we're going to multiply dt over to the right side. So we'll get dv over g minus bv over m equals dt. So we have successfully separated our variables. We've gotten v onto one side of the equation and dt onto the other side. And the reason this works well is you can actually think of this sort of as like we've got a constant times dv and a constant times dt. In this case, our constant is, on the left side, 1 over g minus bv over m, and on the right side, our constant is 1 times dv, or times dt. And of course, we don't want dv, though. We want v, and we want not dt, but t, and so we're going to integrate both sides. And so the right side, that's easy. So the integral of dt is going to be t. And then we have a choice here. We can either evaluate this either as a definite or an indefinite integral. They both work. It doesn't matter which one you do. They're both going to work. I'm going to show it as the definite integral because that is going to sort of incorporate our boundary conditions and hopefully make things a little bit clearer. So we are starting at time 0. So t naught is going to be 0. And then we're going to some time t, and because we want to, in the end, have an expression for what's happening at time t. And so we're going to be going from our initial velocity, which is 0, up to some final velocity, v. And in the end, we're hopefully going to have an expression for v as a function of time. Now, you could do this as the indefinite form with the constant, and that's fine. You would then just use these boundary conditions to figure out what your constants are, and that's absolutely fine. But in this case, if we integrate dt, we're going to get t evaluated from 0 to t, which is just t. Okay, cool. So the right side's easy. The left side, it's just less pleasant. And so the way that you approach this is with a u substitution. At this point, or actually at any point, if if you got stuck before and you didn't get an answer, you realized that you did something wrong in your approach, you should try to work ahead and solve the problem. So if me showing you that, hey, we're going to separate our variables, we're going to integrate both sides, and you need to do a U substitution over here, if that has jogged enough in your memory to remember how to do this, you should pause right now and see if you can finish solving this. And then I'll keep going. And again, if you get partway through and you realize that there's something else you can do, pause the video and try that. Okay, so hopefully you've attempted this either originally or you just paused the video and you're trying it now. To do our U substitution here, the easiest way to do this is to recognize, so we're going to do a U substitution. U, we can do G minus BV over M. And that means that this whole thing is going to be 1 over U, and that's fine. And then we're going to get du is going to be, that's just going to go to 0, so negative b over m dv. And so our original expression then is going to be, 1 over u times dv. And so we can see if du is negative b over m dv, that means that dv is going to be negative m over b du. And so we can write the left side of the equation here. Is the integral of, so dv becomes negative m over b du divided by u. So you get another choice here. So there's just two different mathematical approaches that are fine. Since now we're integrating with respect to u, I either need to change my limits of integration to be with respect to u, or I can just sort of ignore them for now and then eventually substitute my g minus bv over m term back in for u. And it doesn't matter. They're going to do the same thing. I don't know offhand which way you've been taught in math class. Hopefully you should recognize that they both work. And so, if we'll just change our limits of integration to match our new thing. So we need to integrate with respect to u, and so we're going to evaluate u at v equals 0. And so we're going to go from g minus b times 0 over m to, at the top, we're going to evaluate it at v. So this is going to be g minus bv over m. And that is going to be equal to, so that's the left side, equal to t. And so let's clean that up a little bit. So I can move my constant out to the front, my m over b. So we're going to have negative m over b integral. So g minus b times 0, well, b times 0 is 0. This is just g. Right? And then g minus bv over m, that stays the same. So my upper limit is g minus bv over m. And then we have what's left then is this 1 over u du. And so, of course, the integral of 1 over u du is the log of the natural log of the absolute value of u. And so we're going to get negative m over b, log of the absolute value of u, evaluated from g to g minus bv over m equals t. And, of course, again, there are different approaches here. So if you, at this point, wanted to replace u with g minus bv over m, and then just evaluate it from 0 to v, our original limits of integration, that's fine. That's the exact same thing. It's just different approach, different way of thinking about it. Exact same thing mathematically. I got an absolute value in here, which I don't like, but you'll notice our u term here, this g minus bv over m, that is, the way we set that up, this is always going to be positive, right? Because over the course of our problem, so that's just the acceleration, which makes sense because I won't go into why it makes sense. But the acceleration is g minus bv over m, and so that's our u value is the acceleration, and our acceleration for the entire problem is either going to be 0 or downwards, which we said is positive. And so the absolute value of u is the absolute value of our acceleration, but since our acceleration is always positive, we can just do the natural log of u. We don't need to worry about the absolute value signs, and so that's going to make things a little bit easier. So maybe rewrite that without that. And I'm sort of showing like every single possible step here. Obviously, when you're doing your own math, as long as there are enough breadcrumbs to follow, that is sufficient, right? Okay, but in our case, u is always going to be positive, and so we don't need to worry about what the absolute value sign is going to do. And so then I'll substitute my two values in. So we're going to have negative m over b times log of my upper limit, or natural log of my upper limit, g minus bv over m, minus the natural log of g equals t. And then you pick your favorite mathematical method to deal with this. I'm going to move the constant over to the other side, so I just have my natural logs on the left side. You can then either use log subtraction to rewrite this as a single natural logarithm, or we can just use the trick of raising both sides, so e to this and e to what's going to be on the right side should be equal to each other to get rid of our logs and deal with it then. They both work. It doesn't matter. As long as you do something that's mathematically valid, that's fine. So let's move the negative m over b over to the right side. So that's going to be negative bt over m. And then here, natural log of this minus the natural log of this is going to be the natural log of this divided by this. So that's going to be the natural log of g minus bv over m divided by g, which of course becomes the natural log of, so g over g is just 1, minus bv over mg equals negative bt over m. And so then we gotta solve this, so we do e to this side, e to this side, and so e to the log of this is just so, e to the log of this, it's just going to cancel out, right? And you're just going to get that, equals e to the negative bt over m. And at this point, we are pretty close to a solution. We just want to solve for v, and so I'll move my, I don't want to do that. Let's move the 1 over to the other side, I guess. So bv over is negative bv over mg equals e to the negative bt over m minus 1. And then I'm just going to multiply by negative mg over b to get v by itself. So we get v equals negative, so that's mg over b times e to the negative bt over m minus 1. If we distribute the minus sign through, we can just sort of flip these, and we'll get this sort of as our final expression. The velocity is equal to mg over b times 1 minus e to the negative bt over m. And so we've done what we set out to do. We have an expression for v as a function of t. So we only have one variable on the right side, which is t. Otherwise, everything else is a constant, so we should be able to plug any value of t in. Although we wrote this in terms of velocity, and it is also the speed because we set it up so that our velocity would always be positive. And so the absolute value of this, which it's always positive, looks exactly the same, is the speed. And so this should be our expression for speed as well. We can check this to make sure this actually works. So we know that at time equals 0, our skydiver has just jumped out of the airplane, and so our velocity should be 0. Well, let's see if that works. So if the time is 0, we get e to the negative b times 0, so e to the negative 0 or e to the 0. Anything to 0 is 1, and so we get 1 minus 1 is 0. 0 times anything is 0, and so that checks out. The other thing is that if we wait long enough, so if we plug like infinity in for the time, we know that we are reaching terminal velocity. And so our velocity, or our speed, should be our terminal speed. Our velocity should be our terminal velocity. And so we should be reaching our terminal speed, and we already solved for what that is, right? So we know that the terminal speed should be mg over b. Let's see if that works. So if we plug infinity in here, so we get e to the negative infinity. So that's 1 over e to the infinity, which is going to be 1 over infinity, which is 0. So 1 minus 0 is 1. 1 times mg over b is mg over b, and so that checks out. And so both of our limits do exactly what we expect. It behaves the way we expect it to at time 0. It behaves the way we expect it to at time at infinite time. And if we were to actually plot this, remember that a graph that we predicted in the first place is that we should start at 0 and we should asymptotically approach our terminal speed, which is mg over b. And if you plug this into your graphing calculator, think about what it's going to look like, it will indeed do exactly that. And so that has to be the correct expression.